For today's notes, we're going to talk about free fall. When we talk about objects in free fall, we are saying that the only force acting on these objects is the force of gravity. That means that if we're dealing with an object in free fall, that we are going to neglect things like air resistance. We're assuming there's no air that would cause an object to move any differently. So an object in free fall could be an object like a ball. It could be a ball dropped from rest. It could be a ball that is thrown up or down in the air. It could be a ball that's been launched like a projectile. It doesn't have to be a ball, but it has to be an object that is no longer being affected by any forces other than gravity. So in the animation that you see here, this ball is considered to be in free fall once it is no longer touching the person's hand. So the moment that it leaves their hand, now the only force acting on it is the force of gravity. Okay, so what do we know about Earth's gravity? We know that Earth's gravity is a field force that pulls on objects, and that the strength of the field is greater the closer you get to the surface, and it weakens with distance. You can think about astronauts in space or in the space station. Okay, they're basically weightless because they're far enough from the Earth, and yet the space station is still in orbit around the Earth. And so there is still the field from the Earth's gravity pulling on that. But as you get farther and farther away from the surface of the Earth, farther away from the Earth in general, then the field is weaker and weaker and weaker. We use a little g as the variable for gravitational field strength. And so when I talk about gravitational field strength, or little g, the units that we use for this are meters per second or meters per second squared. And those units should look familiar because they're the same units that we used last unit for acceleration. So that little g, that gravitational field strength, measures acceleration due to gravity. And on Earth, at sea level, we will use the value 9.8 meters per second squared. Okay, so that little g measures acceleration. Okay, it measures the acceleration due to that gravitational field, and it has a direction because acceleration is a vector. Okay, and so what direction is that going to be? Well, you can see it in my image over here as well. But when we talk about gravitational field strength, or if you think about Earth's gravitational pull, it's always pulling toward Earth's surface. And so depending on the scenario that you're using, you might define toward Earth's surface as your positive direction, or you might define it as your negative direction. But your little g, your gravitational field strength, or your acceleration due to gravity, will be 9.8 meters per second every second toward the surface of the Earth. Okay, and for this course, we're going to assume, at least right now, that we are close enough to Earth's surface that we can get to always use this value. Okay, once we deal with other planetary bodies and we move in space and we're farther away, it's not this simple. But as so long as you're on the surface of the Earth, you get to use 9.8 meters per second every second. And so for labs and textbook practice, you're going to use little g as 9.8 meters per second. However, you are encouraged on the AP exam, on your unit tests in this class, to use a rounded value of 10 meters per second squared, or 10 meters per second because it makes your math easier. And when you're taking the AP test, those are valuable seconds. And so you can use this rounded value there. But if you're doing a lab, this is not going to be precise enough for what we want. And so again, anytime we're doing an RA, a lab, please use the more precise value of 9.8 meters per second squared. For these notes today, we are going to restrict our focus to only one-dimensional motion, which means we're only going to deal with objects that are dropped from rest, objects that are being thrown straight up in the air, or objects thrown straight down. Okay, we also later on we'll talk about objects that are thrown forward or at an angle where we have motion in 2 dimensions. But for right now, we're going to deal only with one-dimensional motion in playlist 1 of Unit 2. These objects will be in free fall from the moment they are released until they impact another object. Thus, we will assume there is no air. There's no air resistance. There's nothing acting on these objects once they leave your hand or once they leave whatever it is that launched them. okay, or dropped them, the only force acting on them from that moment is going to be gravity. So we're going to neglect air resistance or any other forces. Because only gravity is acting on these objects, we will use 9.8 meters per second squared for the acceleration these objects are experiencing. All right, so let's talk about an example of dropping an object from rest. Okay, so we have a ball, hold it above, the ground at some height and let go. Okay, you can picture that in your mind, or you can even hold a pencil right now and drop it to your desk. What is the initial velocity of an object dropped from rest? Well, it's in the question. If you drop it from rest, its initial velocity is 0 because it wasn't moving. How fast will this object move 1 second after it's released? Well, that's also in the acceleration value that I gave you. The fact that gravity is 9.8 meters per second every second means that after 1 second, that object will be 9.8 meters per second faster than it was moving the previous second. And if it started at 0, then after 1 second, your object is now moving 9.8 meters per second toward Earth's surface, because only gravity is acting on the object. And so we're going to use little g there. And again, this goes back to, do you understand what it means to accelerate? Is the object dropped from rest going to speed up, slow down, or move at a constant speed? Well, if I drop an object from rest, I already know what's going to happen. It's going to move toward the ground. Okay, so if I call that the negative direction, then it's going to move in the negative direction, and that's the same direction that the force of gravity is acting in, okay, toward Earth's surface. And so it's going to speed up because I know that my velocity is going to be in the same direction as my acceleration, which is this question. What does that tell us about the direction of the velocity of the object and the direction of its acceleration? It tells me that they must be in the same direction. If acceleration and velocity are both moving in the same direction, if I call them both downward, okay, then I will have an object that is speeding up. All right, let's think of the second scenario. What about an object thrown downward? So now instead of releasing it from rest, we're throwing it down. And this actually was one of the questions, or related to one of the questions in your test last week, an object being thrown downward. And several of you missed it because you weren't thinking about the fact that if it's being thrown, that it has initial velocity. And so the initial velocity of an object thrown down is going to be a downward velocity. Okay, it depends on how hard you throw it. Maybe it's, a velocity of 5 meters per second downward. Maybe it's a velocity of 20 meters per second downward. It just depends on that scenario. If the object is thrown down with an initial velocity of -2 meters per second, how fast will the object move 1 second after being released? So you can see here I've already defined the negative direction as being downward. And so that means that how fast is it going to move 1 second after? Well, again, that acceleration due to gravity is also downward. My gravitational field strength is pulling toward Earth's surface. And so 1 second after being released, it's going to be 9.8 meters per second faster in that same direction than it was before. So right now it's -2, 9.8 meters per second faster than that. Again, -9.8 meters per second because it's downward is -11.8 meters per second. Objects thrown downward will speed up in the downward direction as they fall. Again, g is 9.8 meters per second every second, and it's toward the Earth's surface, which is also downward. Okay, because they speed up, we know that the velocity and acceleration are in the same direction, so both of them are down. The third example that we talked about was an object being thrown straight up in the air. So you're going to throw it up in the air, and what goes up must come down, so that if it's a ball, you toss it up in the air, it's going to come right back down, and hopefully you catch it again. What is the initial velocity of an object thrown upward? Well, of course, if you throw it upward, it's going to have an upward velocity. Will this object speed up, slow down, will this object speed up or slow down immediately after it's released, and why? So if you're tossing something up in the air, and again, you can try this with your pencil at your desk if you like, be careful. Okay, but if you're tossing it up in the air, okay, you know that it rises to a certain height where it momentarily stops and then falls back down again. Okay, and I say momentarily, it's basically instantaneous. So you don't see it stop, where it's not a Looney Tunes cartoon, if you guys even know what that is. But this particular object, whenever you throw it in the upward direction, we know that that is in the opposite direction as the Earth's gravitational field. Okay, and so that gravitational field strength is pulling down. We're now going up. We have opposite directions here. It's going to slow down. Its initial velocity is upward, but the acceleration due to gravity is downward. When they're in opposite directions, objects slow down. Because it slows down, it will eventually reach a velocity of 0, stopping momentarily before it begins to fall back down from its maximum height. And then as it starts to fall back down, it will speed up because now its velocity is downward and its acceleration is downward, and they're in the same direction. So you will get faster. Notice acceleration does not change. It is always 10 meters per second squared, or 9.8 meters per second squared if we're being more precise. But that acceleration is a constant value. So long as we are at or near the Earth's surface, we're always going to use that 9.8 or that 10 if you're rounding it. Okay. Time of flight is the total time in the air. Okay. And so we can break this up whenever we start to do calculations with free fall, and you have objects being thrown upward. There's a certain amount of time it takes for the ball to rise to the top, and then there's a certain amount of time it takes for it to fall back down. And as long as you are throwing the ball and catching it at the same height, okay, then those times are going to be equal. Time up will be equal to time down, okay, because distance up equals distance down. If it rises, to a height of 20 meters, then it's going to fall from a height of 20 meters back down, and you have the same acceleration the entire time. And so the time it takes to go from this initial velocity that you've given it up here to this 0 velocity at the top will be equal to the time it takes to go from 0 back down to that velocity at the bottom. Okay, but if you find or calculate just the time up or just the time down, you can double it and get your total time, or the sum of the two will be your total time. Again, you only double it if you are catching it at the same height that you released it. Let's do an example problem. This one says, a 0.14 kilogram ball is thrown down at a speed of 3 meters per second from the 4th floor. You time the ball until it reaches the 1st floor. If it took 1.4 seconds, how tall is the 4th floor? So this is going to be the same process that we went through in the last unit with kinematics problems. And you're going to go through the same steps. And so the first thing that you want to do is to identify your positive or negative direction. Okay, in this case, I'm going to go ahead and say that down is negative, and of course that means up is positive. And so I've defined my direction. Down is negative. Okay, so your first step is that. Your second step is to determine what portion of the motion we're examining, and we're examining from the 4th floor all the way to the 1st floor. So this entire thing, there's not different pieces of it here to examine. I know some of the problems last time you had a portion where you had acceleration and then a different portion where you had constant velocity. We're not dealing with that. This is the entire motion of this ball. Okay, and so we're looking at the ball just after release to just before it hits the floor when it's in free fall. We're not looking at when it's on the floor. We're not looking at when it's in the hand. We're only looking at it when it's in free fall. So the only force acting on it the entire time that we're examining it will be the force of gravity. Okay, and our next step is to start labeling our variables. And so if I take a look at the question, I can see that I have an initial velocity, V naught, of negative 3 meters per second. And I know that that's negative because I just defined the direction before I got here. And I said down is negative. And so it's thrown down with an initial speed of negative 3 meters per second. The other next thing that I see is a time, 1.4 seconds. And so I'm going to go ahead and label that as my time. I know that the acceleration in this example, because I'm only looking at this object as it's in free fall, we're going to use little g. And because I defined down as the negative direction, we're going to use negative 9.8 meters per second squared for our acceleration due to gravity. Okay, I don't have an initial position given to me, okay, but it would make sense to call my final position 0. Because I know that I'm dropping this to the floor, so let's go ahead and call the floor 0. We're trying to figure out how tall the 4th floor is, so we're actually looking for x naught. Okay, what was the initial position when it was thrown down? Now it's at 0 once it's on the floor. We don't have the velocity given to us here, but we actually don't have to have it in order to answer this question. If you take a look at your equation sheet and you look at your kinematic equations, you're going to be looking at the same 3 equations that we used in the last unit. And you should be able to pick the appropriate one based on these variables that you've just labeled and the one that you're looking for. And this would be the one that you would want to go with. X equals x naught plus v naught t plus 1/2 at squared. Again, we're ultimately trying to solve for x naught, so let's go ahead and rearrange this equation and isolate that variable. Okay, so if I want to solve for x naught, I need to get it by itself, so I'm going to go ahead and just subtract everything else from this side and move it over here. So I'm going to subtract v naught t from both sides. That'll cancel here. I'm going to subtract 1/2 at squared from both sides. That'll cancel here, and that will leave me with just x naught, and then all of this on the other side of that equation. This is what that looks like. X minus v naught t minus 1/2 at squared equals x naught. Now that we have our equations set to equal the variable that we're looking for, we can substitute in and solve for our answer. If we plug into our equation, x is 0, v naught is -3, time is 1.4, so here's that piece, and then 1/2, my a value is -9.8, and then t squared. So that's what goes into your calculator. Obviously, you can ignore this 0 here. -3 times 1.4 is -4.2. 1/2 times -9.8 times 1.4 squared gives me -9.604. Pay close attention to these signs because I have minus a negative and then minus a negative. Okay, and so that ends up being this, 4.2 plus 9.604 equals x naught. And if I add those two values together, I get 13.8. That is rounded, obviously, 13.804 meters. So the height of the fourth floor in this particular question would be 13.8 meters. That concludes our notes on free fall. So you have, if you have any questions, let me know, but you have some things you can be working on in playlist 1 for unit 2, task options and/or a checkpoint where these notes might come in handy. Let me know if you have any questions.